Hello friends, welcome back to my YouTube channel. In this class I am going to discuss two numericals which are based upon the concept of entropy generation. So before starting I must say one thing to all of you, please do subscribe to this channel, of course like it and share it to your friends. So let's get started. The first question is like this. Consider a steady heat transfer through a 5 meter into 7 meter brick wall of a house of thickness 30 cm. On a day when the temperature of the outdoors is 0 degrees Celsius, the house is maintained at 27 degrees Celsius. The temperature of the inner and outer surfaces of the brick wall are measured to be 20 degrees Celsius and 5 degrees Celsius respectively. And the rate of heat transfer through the wall is 1035 watt. Determine the rate of entropy generation in the wall and the rate of total entropy generation associated with this heat transfer process. Entropy is generated only during an irreversible process. Of course, irreversible process takes place when the heat transfer takes place through a finite temperature difference. In all these cases, there is a finite temperature difference, so there will definitely be some entropy generation during the process. So that's what we are required to find out in this question. So the figure is like this. You see, the room is to be maintained at this temperature 27 degrees Celsius. These are the key points. Room temperature is to be maintained at 27 degrees Celsius, whereas the outside temperature is at 0 degrees Celsius. So, how can we maintain the room temperature at this level when the outside temperature is 0 degrees Celsius? Obviously, heat will flow, so its temperature inside the room will go down. So that's why you have to supply consistently, you have to supply heat continuously through this room and out towards the wall. So heat is flowing in this direction. So heat is flowing in this direction from inside the room to the outside. So that's why to the temperature inside the room will be maintained. So once the heat flow is continuously done, then only the room temperature will be maintained at a high temperature level. Otherwise the temperature of room will go down. If you don't supply heat from outside, due to temperature difference, heat will flow from high temperature to low temperature, and with the passage of time the room temperature will go down. But our objective is to maintain the room temperature at this level. So for that we have to continuously supply heat, and heat flow, direction of heat flow is like this. So whatever heat is flowing here, this is the wall, and at one side of the wall whatever heat flows, that same amount of heat also flows outside the another side of the wall, and that magnitude is 1035 watt. That is given in the question, 1035. This is q dot, rate of heat transfer. So this is given here, 1035 watt. And this inside temperature of the room is 27 degrees Celsius, and this side of the wall, brick wall, is at 20 degrees Celsius, and another other side is at 5 degrees Celsius. This is the temperature of the wall on the other side, that the side of the wall that is exposed to surrounding, and this is the side of the wall that is exposed to, that is inside the room. And so temperature is continuously decreasing in this direction. Here it is 27 degrees Celsius, this temperature is 20, this temperature is 5, and outside is at 0 degrees Celsius, and obviously heat flows in the direction of decreasing temperature. So we have to calculate first entropy generation inside the wall, and then total entropy generation. So before that we must make certain assumptions. So before solving problem we must make certain assumptions. So assumptions are like this. You see, assumptions are like this. First assumption is the process is steady. the process is steady, and thus the rate of heat transfer through the wall is constant. So you see from the figure, whatever heat flows in this direction, here inside the room, and whatever heat crosses the one side of the wall, the side of the wall which is inside the room, this heat is flowing in this direction. Inside the room, temperature is 20 degrees Celsius. The side of the wall, temperature of the wall which is inside the room, and this side of the wall is exposed to atmosphere which is at 5 degree Celsius. So heat is continuously flowing in this direction, same amount of heat. Here also the amount of heat that crosses the wall from inside the room is 1035 watt, and the same amount of heat also goes out of the wall towards the outside. So here also 1035 watt heat flows in this direction from inside the room towards the wall, inside part of the wall. And then that heat also flows through the thickness of the wall, and then it goes outside the wall towards the out surrounding. So heat is flowing in this direction. This amount of heat is flowing in this direction because this is a steady flow. In steady flow there is energy conservation principle is followed. So whatever amount of heat flows here must also go out of the other side of the wall also towards the surroundings. So that is the first assumption we should make. And then second assumption is heat transfer through the wall is one dimensional. Here heat is flowing in only one direction through the wall, so there is no heat transfer in the perpendicular direction to the wall. So that's why it is a one dimensional heat flow. So now we have to apply the entropy balance for the wall to find out entropy generation in the wall. First bit in the question, it is you are required to find out entropy generation in the wall. So for that we have to apply principle of entropy balance. You have to apply the principle of entropy balance to the wall. You see here in this case, wall is a closed system. Because through wall no mass interaction takes place. Nothing enters into the wall and nothing evolves out of the wall as far as mass is concerned. Only energy interaction can take place in form of heat here, and so that means your brick wall can be taken as a closed system. So if you apply the entropy balance equation in rate form, the equation will be like this: S dot in minus S dot out plus S dot gen. This is rate of entropy generation inside the wall. This is equal to all these terms are expressed in rate form. So that's why ds upon dt. This is change in entropy with respect to time, or you can say rate of change of entropy, and this is 0 for steady flow process. This is already we have assumed that this is a steady flow process. So for steady flow process, if you find out derivative of any property with respect to time, it will be 0. So ds upon dt, that is rate of change of entropy or change in entropy with respect to time, will be 0 because this is a case of steady flow. What does this term represents? This is nothing but rate of net entropy transfer by heat and mass. In entropy balance, these two terms represent rate of net entropy transfer by heat and mass. This is totally rate of entropy that enters into system. This is the rate of entropy that is going outside the system. So if you subtract this from this, you will find the rate of net entropy transfer by heat and mass. But this is a case of closed system, so there is no question of entropy transfer by mass, because there is no mass interaction takes place in case of a closed system. So there is no question of any entropy transfer with mass. Only in this case entropy can be transferred from outside the surrounding or towards the surrounding only by heat, because only heat interaction is taking place here. So now I can write like this: q dot by t in minus q dot by t out. This is s dot in, this is s dot out, plus s dot gen and rate of entropy generation within the wall. This is 0. You see here q dot is given in the question, that is 10. Q dot means rate of heat flow, which is given to be 1035 watt, divided by, this is the temperature at which the heat enters into the wall. That temperature is 20 degrees Celsius. Here we are interested in finding out the entropy generation within the wall only. So that means here T at this point is 20 degrees Celsius, and you have to express that in terms of Kelvin. So 20, here the heat is entering, q dot by t in, matlab t will be 273 plus 20, that is 293, minus 1035 watt. This is again T dot out, the temperature at which the heat is going outside the wall. This is the wall, this is the wall. Here at 20 degrees Celsius heat enters into wall, and at 5 degrees Celsius heat goes out of the wall. And in 5 degrees Celsius, if you convert that into absolute temperature, that will be 278 Kelvin, plus s dot gen equal to 0. So rate of entropy generation, rate of entropy generation in the wall will be, from this equation, that will be minus 1035 is equal to 0.191 watt per Kelvin. This is rate of entropy generation in the wall. 0.19 watt per Kelvin. This is one of the questions that has been asked, that is the rate of entropy generation in the wall. But how to calculate the rate of total entropy generation associated with this heat transfer process? So how to calculate the total entropy generation? Not only inside the wall, the total entropy, here only the entropy generation in the wall is this much that we have calculated, but how to calculate the total entropy, rate of total entropy generation associated with this heat transfer process? This process takes place from inside the room to outside, not only through wall, but in the whatever answer we calculated is the entropy generation within the wall. Now we have to extend the system. We have to take the immediate surroundings of the wall. We have to extend the system to calculate the total entropy generation during the process. Extended system here will include regions on both sides of wall, प्लस वॉल इज ऑलरेडी देयर, वॉल के साथ ये रीजन को भी हमको एनालिसिस पे लेना है। रीजन्स ऑन बोथ साइड्स ऑफ वॉल, कुछ रीजन तो रहेगा इमीडिएट सराउंडिंग, दिस इज कॉल्ड इमीडिएट सराउंडिंग। एक्सटेंडेड सिस्टम में हमेशा हम इमीडिएट सराउंडिंग को लेते हैं। सो हियर इमीडिएट सराउंडिंग मीन्स some region within the room and some region outside the room which are close to the wall, so that is called immediate surrounding. So this is the regions on both sides of wall, and those two parts or those two regions are called buffer zone. So if we take those regions into account, now our entropy balance equation will be 1035 q dot by t, same heat is flowing through the system, through the process. Here also the same, inside the room also that same amount of heat is flowing, but temperature is different. Here the in temperature will be at 27 degrees Celsius inside the room. Here the heat, while heat is flowing in the immediate surrounding, the temperature at which heat enters into this extended system is 27 degrees Celsius or 300 Kelvin. So our equation will be 300 Kelvin minus 1035 watt divided by, and this temperature at the other extreme, that is outside temperature, is 0 degrees Celsius. This is not the wall temperature. The other side of the wall is at 5 degrees Celsius, but this is the surrounding, and this temperature will remain constant throughout the process. Whenever we will take the extended system into consideration, this will be our boundary temperatures, 27 degrees Celsius and 0 degrees Celsius. In terms of Kelvin, this will be this much, plus rate of entropy generation is equal to 0. This is total. That was entropy generation in the wall. This was entropy generation in the wall. This is entropy generation in the wall, but this is total entropy, rate of total entropy generation. This is equal to 0. This is 0. On equating this, rate of total entropy generation will be 0.341 W per watt per Kelvin. It is definitely higher than 0.191. This is 0.341 watt per Kelvin, and when we calculated entropy generation within the wall was 0.191. So the difference is 0.150 watt per Kelvin, because during the process this much of entropy is generated on the both side of wall, So 0.19 watt per Kelvin is the entropy generated within the wall, and extra 0.150 watt per Kelvin is generated if you take the entropy generation in these two sides which are close to the wall. One side is within the room and the other side is in the outside the room, but close to that side of wall, brick wall. So in the immediate surrounding of brick wall, some entropy is generated because there is some finite temperature difference. Here temperature is 27 degrees Celsius, here temperature is 20 degrees Celsius. So the finite temperature difference, whenever heat transfer takes place through finite temperature difference, means this is an irreversible process. Entropy is generated during only during an irreversible process. So the point to remember is that during reversible process no entropy is generated. So, and other side of the wall also some entropy is generated, because here the temperature of the wall is 5 degrees Celsius, but this side's temperature is 0 degrees Celsius. This, due to this finite temperature difference, some entropy is also generated. Due to finite temperature difference, entropy is generated because this is an irreversible process. So total entropy generation is 0.341 watt per Kelvin. The next question is Next question is like this. A 50 kg block of iron casting at 50 degree 500 Kelvin is thrown into a large lake that is at a temperature of 285 Kelvin. ये जो ब्लॉक ऑफ आयरन है उसका टेम्परेचर 500 केल्विन है and it is thrown into a large lake that is at a temperature of 285 Kelvin. The iron block eventually reaches thermal equilibrium with the lake water. Assuming an average specific heat of 0.45 kilojoule per kg Kelvin for the iron, determine the entropy change of the iron block, then the entropy change of the lake water and the entropy generated during this process. So जो आयरन ब्लॉक है उसका टेम्परेचर 500 केल्विन है एंड इट इज थ्रोन इनटू ए लार्ज लेक whose temperature is at 285 Kelvin. Obviously heat will flow from iron casting to lake because the iron casting is at a higher temperature. But one important thing to know that the whenever heat flows from one body to other, one's temperature decreases and the temperature of other body increases. But here in this case, since lake is a large body, its thermal capacity will be higher. So that's why no matter whatever heat may flow from iron casting to the lake, the temperature of the lake will not increase. It's a different thing that the temperature of iron will decrease, and eventually here the equilibrium temperature will be 285 Kelvin only, because the lake is a reservoir. Lake will play the role of reservoir here. So the final temperature is going to be 285, but heat will flow from iron to lake, but temperature of lake will not increase. So we have to find out first the iron block entropy change, then entropy change of lake water, and the entropy generated during the process. This is the figure is like this. The iron casting is at 50 kg of 50 kg mass and temperature is 500 Kelvin, and lake is at 285 Kelvin, and this casting is thrown into this lake. So to solve this question, first we have to make certain assumptions. First assumption is that both water and iron block are incompressible substances. Incompressible means their volumes don't change with change in pressure or temperature. Then second one is constant specific heat. Specific heats can be used for water and iron. So these are the assumptions. First, we have to take the iron as the system. We have to take iron casting as system. We'll take iron casting as system for our analysis so that we can find out its entropy change. So you see, if this is iron casting is considered as a system, it is a closed system. No mass transfer takes place between lake and iron. Nothing can enter into iron casting and nothing can also get out of this casting. So this is a closed system. Only energy interaction can take place. Only heat can flow from iron casting towards lake, because the temperature of iron casting is 500 Kelvin and the temperature of lake is 285 Kelvin. So heat will only flow in this direction. Q will go in the outward direction only. So you see, if you want to calculate the change in entropy of iron, in the first bit you are required to find out change in entropy of iron. this is nothing but m into this is small s2 minus s1. This is change in specific entropy. This is we are required to find out. For that, you see, in this case only entropy transfer is taking place through heat transfer only, because iron casting is a closed system. Iron casting is a closed system. So delta S, there is no entropy. In fact, the change in entropy will be, change in entropy of iron will be calculated on the basis of the equation that you know, delta S is equal to, first we have to find out the final temperature of iron. Final temperature of iron, because you see, when iron comes into thermal equilibrium with the lake, only the final temperature will be lake, the temperature of lake will not change. So final temperature here will be T2 will be 285 Kelvin for both iron and lake. So T2 will be this much. So that means delta S will be mc ln T2 by T1. This is the formula. Whenever a solid or liquid body is there, if you want to calculate the delta S of that body, the formula is like this. Of course, but not for reservoir, only for a simple body. Here iron casting is not a reservoir, so that's why we can use this formula mc, where m is the mass, c is the specific heat, and assuming that the specific heat does not vary with temperature, mc delta S is equal to mc dt upon t, and if you integrate this, then this formula comes out. Delta S iron is equal to this much, mc ln T2 by T1, and this is coming out to be 50 kg multiplied by 0.45 multiplied by ln 285 divided by 500 Kelvin, and this comes out to be minus 12 point. This is in fact the ds is equal to mc dt, and delta S ds is equal to dq upon t. So that's why mc dt by t, and on integrating delta S will be this much. Delta S will be mc dt upon t, because this m and c are constant, they can be taken outside. So delta S is equal to mc integral of dt upon t. This comes out to be minus 12.65 kilojoule per Kelvin. So next bit is, you are required to find out, determine the entropy change of the iron block. So that's why entropy change of iron block is this much, minus 12.65 kilojoule per Kelvin. Then we are required to find out entropy change of the lake. So to find out the entropy change of lake, we have to calculate what is the amount of heat that is going towards lake from the iron casting. For that, we have to use the energy balance equation. For the energy balance equation is like this: E in minus E out is equal to delta E of system. You see, we have taken iron block to be the system. Iron block, we have used the iron block as the system. So E in matlab E in minus E out here will be net energy transfer. ये किसी सिस्टम और सराउंडिंग और दोनों सिस्टम के अंदर एनर्जी इंट्रैक्शन जब होता है, energy interaction takes place through three modes. One is heat, one is work, and another is through mass. But here, since iron casting is a closed system, no energy interaction can take place with mass. So only in energy interaction that can take place is through heat and work, but there is no work transfer here, so only heat interaction is taking place, and the heat is going outside the iron block towards the lake, because this is at a high temperature. So Q out, only heat is going outward, is equal to delta E में जो होता है there are three terms, delta ek plus delta ep plus delta u. Since this iron casting is stationary, so delta ek plus delta ep will be 0. Delta ek plus delta ep will be 0 for this iron casting, and so delta e will be delta u only, change in molecular internal energy. So this is equal to delta u, and delta u is nothing but mc delta t. Delta u is nothing but mc delta t, mass into specific heat, and delta t is T2 minus T1. But you see, from this equation, q out, whatever heat is rejected can be calculated, and this is mc T1 minus T2, and this will come out 50 kg multiplied by 0.45 kilojoule per kg multiplied by 500 is the initial temperature minus 285. 500 is the initial temperature T1 minus 285 Kelvin. This will come out to be 4858 kilojoule. This amount of heat is going outward from the iron casting towards the lake, 4858 kilojoule. So, but we are required to find out in the second bit the entropy change of lake. Since a lake is a reservoir, in case of reservoir, how to calculate entropy change? Only in case of reservoir, no change in temperature takes place. The temperature of lake or temperature of reservoir always remains constant. So only if heat is coming to a reservoir, then entropy change will be plus q by t, the temperature at which the reservoir remains constant, and if heat is going out of a reservoir, the entropy change will be minus q divided by the t at which the temperature of reservoir is constant. So in this case, entropy change of lake will be positive, because heat is going towards lake, that is q lake, whatever heat is going towards lake divided by temperature of lake, that is 4838 plus, of course, heat is going towards the lake, so this is going to be 16.97 kilojoule per Kelvin. This is entropy change of lake. So entropy change of lake is positive, but in the first bit we calculated entropy change of iron casting is negative, and we are now required to find out entropy generated during the process. Not only in the iron block, nor in the lake water, but also the total entropy generated during the process we are to calculate. For that purpose, we have to take the extended system into consideration. Extended system is not only iron block, but the immediate surrounding. Some surrounding will be taken under the analysis. This will be our system. And boundary temperature will be 285 Kelvin. Boundary temperature will be taken, and this total extended system will be taken into consideration rather than this iron casting only, and this region outside this iron block will be called buffer zone, and entropy change of this buffer zone is neglected with respect to entropy change of this iron casting, and we can apply entropy balance equation for this extended system, and the boundary temperature for analysis purpose will be taken to be 285 Kelvin always. So now if you apply the entropy balance to extended system, entropy balance, to calculate the entropy generation during the process, you have to apply entropy balance principle, which will be more convenient. Entropy balance equation for extended system will be S in minus S out plus S gen is equal to delta S system. In this case S in कुछ नहीं है, यहाँ कोई भी किसी तरह के एंट्रोपी ट्रांसफर अंदर से नहीं, अंदर की ओर नहीं हो रहा है, क्योंकि हीट इज गोइंग इन दिस डायरेक्शन. सो ऑब्वियसली सम एंट्रोपी इज ट्रांसफर्ड आउट द सिस्टम. It is flowing out, the heat is flowing out of the system. So entropy will be transferred out of the system. यहाँ नेट एंट्रोपी कुछ आ नहीं रहा है, वो जा रहा है. सो एंड दैट विल बी, देर इज नो मास ट्रांसफर ऑल्सो. सो माई एस इन तो नेग्लेक्ट हो जाएगा. एस आउट में माइनस क्यू आउट डिवाइडेड बाई टी बी प्लस एस जेन इज इक्वल टू डेल्टा एस system, or Sgen will be delta S system plus Q out by TB. This will be डेल्टा एस सिस्टम. मतलब यहाँ जो एक्सटेंडेड सिस्टम हम ले लिए हैं, ये वी हैव टेकन द एक्सटेंडेड सिस्टम टू बी आयरन कास्टिंग प्लस इमीडिएट सराउंडिंग, बट delta S system will be same as delta S of iron casting only. Here the entropy change of buffer zone is neglected with respect to entropy change of the original system. In case of analysis of extended system, what we do is we neglect the change of buffer zone that is around the iron casting. So here delta S system will be same as delta S of iron casting, delta S of original system. Delta S of extended system is always equal to delta S of original system. So that is delta S of iron, delta S of iron casting plus Q out by TB. So this is equal to minus 12.65 kilojoule per Kelvin is delta S of iron casting, we have already calculated, plus 4838 is the amount of heat that is going out of the iron block, kilojoule divided by 285 Kelvin. So this is coming out to be 4.32 kilojoule per Kelvin. So this is entropy generation, and entropy generation can never be negative. It is positive or zero. So second law is satisfied here. Entropy principle is satisfied here because it is positive, means this is an irreversible process. In case of ideal process, entropy generation is zero, and this whole problem can also be solved. This entropy generation can also be calculated by taking iron block and entire lake as system, which is an isolated system. If we take iron block instead of taking iron block and immediate surrounding into analysis, if we take iron block and whole of this lake as your system, that can be considered as an isolated system. If iron block is taken and lake is taken, so there is nothing left out. So this is your universe, but this will be an isolated system because there will be no kind of interaction, neither mass nor energy interaction. And in that case, if you apply the entropy balance principle to that extended system, isolated system, this is S in minus S out plus this is entropy balance principle, this is equal to delta S. Suppose this is isolated system or the combined system that is taken into consideration by taking iron block and the whole lake, but in that case these two term will be zero because this is an isolated system. So neither कुछ एंट्रोपी आएगा नॉर कुछ एंट्रोपी बाहर जाएगा, क्योंकि आइसोलेटेड सिस्टम का मतलब देर इज नाइदर मास इंट्रैक्शन नॉर एनर्जी इंट्रैक्शन. एंट्रोपी ट्रांसफर कैन टेक प्लेस ओनली विथ हीट और मास. So if there is no interaction, then these two term will be zero. So entropy generation will be only delta S of. So entropy generation will be delta S total. Delta S total matlab delta S of iron plus delta S of lake, which we have already calculated. And so entropy generation will be minus 12.65 plus 16.97, that is 4.32 kilojoule per Kelvin. So in both these ways we can solve. either extended system लेके analysis करेंगे, नहीं तो isolated system लेके analysis करेंगे. extended system मतलब iron block और कुछ region immediate surrounding को लेंगे और entropy balance लगाएंगे. You see here iron block and immediate surrounding को लेके extended system, Otherwise we can take iron block and the whole lake as the isolated system, and we will apply the principle of increase of entropy. That is, the entropy of an isolated system always increases. So delta S total will always be positive. And then you can also apply the entropy balance principle and calculate the entropy generation. Entropy generation in that case is same as delta S universe if you take isolated system into account. So entropy generation is equal to delta S universe, that is equal to delta S system plus delta S surrounding. Here two systems are there, iron and lake. So individually we will calculate delta S of iron and plus delta S of lake, which we have already calculated, and thus add them though to find out the entropy generation during the process. Otherwise we can apply the entropy balance principle to the extended system, that is that takes iron casting and the immediate surrounding into account, and in that case boundary temperature remains constant at the lake temperature, that is 285 Kelvin. So that's all.